Welcome to lecture 3. Let's cover scalars, vectors, and tensor calculus. So scalar has magnitude but no direction. An example is pressure P. A pressure P is a scalar quantity. And the coordinates of a Cartesian space could be x, y, and z, and they're considered scalars. Some people use x1, x2, and x3 instead of x, y, and z. A vector has both magnitude and direction. And typically ij and k denote the unit vectors in the x1, x2, and x3 directions. Here in this plot, we're showing x, y, and z, but you could use x1, x2, and x3. Some other people, instead of using ijk as a unit vectors defining this Cartesian coordinate system, may use e1, e2, and e3. The magnitude of these unit vectors is 1. A position vector is typically defined to a particular point in the space, and that position vector is called x with a vector symbol in the top. X, y, and z are the values along the I, j, and k correspondingly. An independent, these vectors are independent of coordinate system. It doesn't matter what coordinate system I'm looking at, the vector will have the same magnitude in the same direction as well. You could also have spatial vectors versus position vectors. So say you have a velocity field v. This velocity field v is a spatial vector. The vector that goes from the origin to where this vector starts, we call this a position vector. A scalar can be a function of vector. For example, this pressure here can be a function of this vector x. The same with velocity of the flow. A scalar is a zero-order tensor, and that was discussed in the previous section. A vector is a first-order tensor, and a matrix is a second-order tensor. An example of a second-order tensor is stress. An example of a scalar quantity is temperature. That's a zero-order tensor. A vector velocity, as an example, is a first-order tensor. A force is a first-order tensor. It has a magnitude, and the force has a direction. Another way to write a vector is in Cartesian form. So you could write x with a vector symbol on the top, xi hat plus y, j hat plus zk hat. That's one approach. The coordinates x, y, and z can also be written as x1, x2, and x3. So instead of using x, y, and z, like I said before, you can use x1, x2, and x3. The vector in this case is x with the vector symbol on the top, and then x1, x2, and x3 are the components of that vector. And you can write that as x1, e1, with e1 being the unit vector. So basically we're saying that this vector x has a component of x1 in the e1 direction, has a component of value x2 in the e2 direction, and then x3 in the e3 direction. Since 1 and 2 and 3 are repeated on both sides here, you could write this in Euler notation. So that will be xi, ei. So here, I is understood to be a dummy index. A scalar operation alpha a with a vector in the top is alpha ai. So alpha distributes to each of the components of a, of this vector a. The dot product or scalar product of two vectors results in a scalar. A vector dotted with b vector is equal to a1 b1 plus a2 b2 plus a3 b3. So the components of a multiply the component of b correspondingly, and then you get a scalar quantity. In index notation, a dot product will take this form. It will take AIBI, or it could be AKBK or ARBR. And the reason that works is because I is a repeated index. So it would be summation of I over 3, or you could just change it to K. It doesn't matter. It's a dummy index. The bottom line is, since that the index is repeated, that you're allowed to, you can change it if you want. The repeated index typically without the summation means summation from the value R1 to 3. The Einstein summation convention, if the same index occurs twice, always sum over that index. So here, AIBI, AKBK, ARBR is the same. There's no free index here. You can see that. So therefore, this must be a scalar quantity. Let's look at the magnitude of a vector. The magnitude of a vector, A hat squared. So you have A hat. So you're looking at the magnitude of this squared. That's A dot A. So that's AI. A tensor can be constructed by performing the outer product of the two vectors. So say I have a vector AI and a vector B. So a vector A and a vector B. The outer product of these two vectors gives you a second order tensor. And EI and EJ correspond. AI and EI is the one vector. BJ and EJ is the other vector. And then this right here, this is considered the outer product of these two vectors. And so the components will look like this. Consider that you have AI, AJ, BJ. In this example, since J is repeated, then this is a second order tensor as well. Let's look at the dot product of two vectors. So if one vector U is UI, EI hat, and the second vector is VJ, EJ hat, then I can rearrange. I have UI, VJ here, and then EI hat dot EJ hat. Notice that if EI is dotted with EI, I should get 1. If EI is dotted with EJ and I is not equal to J, I should get 0. So because it's orthogonal, right? So the dot product of two orthogonal vectors is 0. The dot product of the vector on itself is 1. So clearly, this must be the Kronecker delta del ij. And so you can cancel out J to get I moved over, UIBI, which is the result we got earlier here. We got the same thing here, right? But I did it with different variables. I defined this earlier, but Kronecker delta is del ij. You know, if I is equal to J, then it's 1. If I is not equal to J, you get 0. So you get a diagonal of 1. Since there are two indices, the result is a second order tensor. The third order Levi-Civita tensor, epsilon ijl, is equal to 1 if you have 1, 2, and 3 here as indices, 2, 3, 1, or 3, 1, 2. You get -1 if you cycle counterclockwise, and you get if it were to be 1, 3, 2, 2, 3, 2, 1, that's an error, or 2, 1, 3. Otherwise, you get 0. If any of these indices are repeated, you get 0. Here's an important identity. In my book, I go over this identity and prove that this is indeed correct. Here, what I need to notice is that I is repeated and nothing else here is repeated. So this is a fourth order tensor, and you'll see here that this is what you'll get. If you were to write it down, you will see that's what you get. The calculation of a cross product, if I have EI hat and EJ hat, the cross product will give you epsilon ijk, and you will have E hat k. So the cross product of two unit vectors gives you the third vector, and it's perpendicular. That vector is perpendicular to these two vectors. And here this symbol comes into play, the permutation symbol. The cross product of two vectors is written as U cross product with V, and you get epsilon ijk. This is the permutation symbol, UI, VJ, EK hat. And you can see here I is repeated, J is repeated, and so therefore you get a vector that comes out of here, this cross product. So let's look at the cross product of two vectors. So you get A with the vector symbol cross B with a vector symbol. That's the same as having CI equals epsilon ijk, AJ, BK. The way you can remember this is if I shows up in the left-hand side, then you're going to put j here and k here. And that gives you exactly what this cross product is. If you were to try it out, you will see it works out. For example, let's take the first term, C1. C1 corresponds to the first component of the vector. So C1, C2, and C3 are the three components of a vector. Let's look at C1. C1 is epsilon 1jk, ajbk. Now that's double summation over j and k. And so I can start expanding. And you will see that, for example, you'll get one of the terms will be 1, 2, 3, A2, B3. Well, this is 1. And you'll get another term that says 1, 3, 2, 3, 2. Well, that's minus 1. And the rest of the terms will be 0. And so you will get C1 to be equal to A2, B3 minus A3, B2. And very similarly, you can do it with C2 and C3. And what you will see is that you will get exactly as what you have expected if you did a cross product of these two vectors. Here I have the gradient. The gradient of a scalar will give you a vector. So here is a gradient of P, for example. But if I were to write this in index notation, I'll have EI bold, which is a unit vector, and then partial derivative of something respect to xi. So the gradient of P, which is pressure, in this case will give you components of the derivative of P respect to x1, the derivative of P respect to x2, derivative of P respect to x3, and these three become the components of a vector in the I, J, and K direction. And here at the bottom is another way to write it, the same thing. Instead of I, J, and K, you can write this out so that it's index notation. It's only summation over I, so I1 through 3. Clearly, that will give you the same as this, because the first term will be E1 x1, which is this, E2 x2, which is this, and so forth. So here's another way to write it out. The gradient of f, here you get the gradient, the partial of f respect to xi. That's f comma I, ei if f were to be a scalar. And so you get what I got here earlier, but written a little bit different. The same thing. So now if I take the gradient of a vector, I'll get a tensor. So the gradient of a vector gives you a tensor. So here's the derivative of fi respect to xj now. So that's fi comma j with the second order tensor symbol here, the outer product. And if I were to arrange it in the matrix, it's going to look like this. In Cartesian, cylindrical, and spherical coordinates, you get this in Cartesian. In cylindrical, you get this, and in spherical, you get this. So if I were to find a gradient of A, for example, I'll get a vector if A is a scalar. So the Cartesian approach looks like this. The cylindrical portion looks like this. And if I were to do a spherical coordinate system, it looks like this. The divergence now of a vector turns the value into scalar. You get a scalar quantity. So the divergence of a vector u gives you the derivative of u1 respect to x1 plus u2 respect to x2 plus u3 respect to x3. Well, that's ui respect to xi. So this divergence lowers the tensor by 1. For example, here the divergence of f, a vector, gives you a scalar quantity. You can see that here. This is the same thing. What I wrote here above is the same as here. I'm just giving you a second example. The gradient of f here now gives you the derivative of fij respect to j. So now that's a vector again. And the vector is given here on the right-hand side. The curl converts a vector to a vector. So a curl of u, for example, if you've never seen that, this happens in vortices. So here I have ijk, and I have the derivative with respect to x1. That's what the gradient symbol means. And so this is put in a vector. I take the cross product against u, which is these terms. And so here's what I'll get, right? So if you cross this column and this row, is I times this minus this. So that's what you get as a first term. And so forth. I'll get the remaining terms. In index notation, this is the way it looks like. And I encourage you to pause the video at this moment and expand this so you can see that you get exactly what you see here. So now you have integral theorems that need to be discussed. Gauss theorem is in relationship between a volume integral over the divergence of a vector f and a surface integral over the values of the field at the surface S. It's a very powerful concept. So let's look at an important theorem that we're going to be using over and over and over. We're going to be using Gauss theorem. And what Gauss theorem does is it takes a volume integral, as you can see here on the left, and then converts that into surface integral. Very powerful concept. It's telling us that if I evaluate this gradient inside the body of the material, that I can understand what's going on inside the body of the material by just examining the surface and evaluating A times the normal of the surface at every point on the surface. Very powerful concept that will be used over and over and over, and I'll be deriving this a little bit later when I do the writing this by hand. Here on at the bottom, I write for you the form in matrix notation. Here, what you see here is that I have the gradient symbol of A. So that's exactly what A comma I is. A comma I are the components of the gradient of A. The gradient A is a scalar, then the gradient of A gives you a vector. On the right hand side, very similar, they have A n hat. Well, n hat is ni. So here, I shows up in the left and right, which makes it an equality of three equations. So I equals 1, and I equals 2, and I equals 3. That's three equations right here. On the right hand side, I have the gradient of a vector. So here, right now I have bi comma I dv. So again, I can take this gradient inside the body and then evaluate, this will be equal to evaluating bi times ni on the surface of the body. Very powerful idea being shown here. So here's other ways you may see it written in different books. You have the green theorem here at the top, which is an essentially very similar to Gauss theorem. So I can convert what's going on in the surface of the body to what's going on inside the body. So surface to volume integrals. And we'll be doing some of that in this course. Here you can see what it will look like if I have a second order tensor. Aij, comma j, we're going to see that with stress. Aij, comma j, that's inside the volume of the material here at the bottom right, if you can see that. And if I know what's going on with the stress, how the stress changes inside the body of the material, or the gradient of stress, then I can know what's going on the surface. So evaluating Aij and j at the surface will be equal to what's going on inside the body. So very powerful idea being shown here. You may also encounter the curl of u dotted with n. And so this will give you a scalar quantity. And if I know this on the surface, I can determine what that is in a curve that encloses that surface. And yeah, it's a very powerful idea. It's a scalar quantity. Here you can see I repeats, j repeats, and k repeats. So clearly this is a scalar quantity on the left. On the right hand side, also the I repeats. And so this should be equal to that. We want to find the determinant of the second order tensor. Here you get, basically this is a determinant of second order tensor. And if you did the calculation, you'll see that you can write this as 1/6 e ijk e abc a ia a jb a kc. And if you expand this, you will get exactly what the determinant should be of a, of a second order tensor A. So I invite you to go ahead and do that. The properties of determinants of second order tensors. So if I find the determinant of I get unity. If I find the determinant of the A transpose, it will be equal to determinant of A. Determinant of alpha A is alpha cubed determinant of A. And the determinant of A dot B gives the determinant of A times the determinant of B. You're also going to encounter problems with eigenvalues. So if I were to have an eigenvalue problem, and I have a second order tensor A dot with a vector n, that'll be equal to lambda A with times NA. So I can factor out NA, and so I get this. So if I were to find a determinant of this here, I can find a way of making this equality equal to 0. So the determinant of this matrix right here, which this is second order A, tensor A, 3 by 3, minus lambda times the identity matrix. If I find that determinant, I'll get a characteristic equation that looks like this. And the characteristic equation that looks like this is going to have these coefficients I, 2i, and 3i, which can be found here. I is the trace of A, so just add the diagonals up. The 3 i's here is just find the determinant of A, and that'll give you that number. And then the second one here is 2a, just find the A and square the trace, or multiply, and then multiply A times A, and then find the trace of that. And that'll give you this. So once you have this, you can find lambdas, and these lambdas, when substituted here, will make this equal to 0. There's also an important theorem that you may find. It's called the Cayley-Hamilton theorem. All it says is if I take this A that's here, and I multiply it by itself 3 times, minus I, which is calculated from here, times A multiplied by itself twice, plus double I times A minus triple I times I, that will be equal to 0. So that will conclude this portion, and then we're going to move into the written portion. So let's consider Cartesian tensors. So let's start with vectors. What are vectors? They're directed lines segments defined by magnitude and direction. And these vectors, examples of that will be velocity, and they can be represented by its components unit basis vectors EI. So in other words, if I have a Cartesian system x1, x2, x3, then this will be the unit vectors. This will be unit vector E1, E2, and E3. Sometimes you may see a convention where E2 is more like this. It's the same thing. And so if we look at the properties of E, of this unit vector E, EI, the magnitude of EI will be 1. And you're going to also have orthogonality. Meaning, if I take EI and dot product with EJ, then that will be the Kronecker delta. Meaning, if it's E1 and E2, then this should be 0 because E1 dotted with E2 is 90 degrees apart. So that should be 0. But if I have E1 dotted with E1, I should get a unit vector. We also have the fact that if I take 2 vectors and find the cross product, I should get the third unit vector. So those are the properties of these basis vectors. And I can now perform operations. So say I have 2 vectors, A and B. So vector A can be written as components of AI, EI. So that's basically A1, E1 plus A2, E2 plus A3, E3. You could also have the components of B, which is B, BJ, ej. I can make it different. I can make it I, whatever I want, but it's repeated. And this is equal also to b1, e1 plus b2, e2 plus b3, e3. So the components of that vector b can be written in that manner. So if I want to find the dot product of a and b, then I have a dot b should be equal to ai ei dotted with bj ej. And all I did here was to substitute this and this into this expression here. Now notice that this is constants, so I can bring it up like that. ai bj ei dot ej dot. Now notice that this right here is a Kronecker delta, which we saw earlier. So that will be ai bj del ij. Now you can take this j, cancel it out, and bring the I over, so you get ai bi. So that's how you find the dot product. And notice how the dot product of these two vectors becomes a scalar quantity. This becomes a scalar quantity. So if I want to find the cross product now of the two vectors, A cross B, then the formula for that can also be found. The formula for that is A cross B, which is equal to, I'm going to get AI BJ, right? And then we're going to have now the cross product of E1. And since I'm going to make it general now, I'm going to say AEIJK EK. So that will be the cross product. And in expanded format, you can find this very easily. You're going to find, sorry about that. You're going to find that this is equal to, if expanded it, A2 B3 minus A3 B2 E1 plus minus A1 B3 plus A3 B1 E2 plus A1 B2 minus A2 B1 E3. Okay, so that's how you find the cross product. I can also determine the angle between the two vectors. So the scalar product A dot B can also be found as a magnitude of A times the magnitude of B and the cosine between these two vectors. So if I know this dot product and I know the magnitude of A and magnitude of B, I can calculate the cosine between the angles. So I'm able to find the angles based on that. Another important thing I want to discuss now is coordinate transformations. Coordinate transformation. So let's consider two Cartesian coordinate system. C and C prime. So I'm going to consider that. And here is one of them, x1, x2, and x3. And I want to figure out, and these are coordinate system C, and then I want to figure out what will happen when I do a transformation. X1 prime, x2 prime, x3 prime, and this is your C prime coordinate system. And so I can now take a position vector r, and remember, position vector r can be represented either in the C coordinate system or C prime coordinate system, but the magnitude of that vector and the direction does not change. So I can now take the position vector r and represent it in one coordinate system. So in the first coordinate system, C is going to look like this, right? And now I can also represent that same position vector as xj prime ej prime. So I can either represent it in C or I can represent it in C prime. Regardless, I can represent it in either of those ways. So what I can do now, I can take the dot product with EK on both sides. So it's a little trick we're going to do. So let's do that. So I have xi ei dotted with ek prime. And then on the other side, I have xj prime ej prime dot with ek prime. And notice how this becomes a Kronecker delta. And this j is repeated. So therefore this right-hand side becomes xk prime. We also notice that we could now use the definition for this. So this right here can be written as xi, and then the magnitude of vi, the magnitude of vk, and the cosine between those two vectors, ei, comma, ek prime. And on the right-hand side, I have xk prime. So this right here, we know is 1, because the magnitude of unit vector is 1. This right here is 1. So therefore, I'm able to find an expression that relates this quantity in the C prime coordinate system to the C coordinate system. So I have xk prime equals xi cosine ei comma eak prime. So you can see there now I have a way of transforming the components of the position vector r, right, which are written originally in this way. I have a way of converting them into the new coordinate system C prime. As long as I know how is it oriented, I can calculate these cosines. I can calculate these cosines if I know how the two systems are oriented next to each other. I'm going to call this here, right here, I'm going to call this, and I apologize, but should be this whole thing. I'm going to call all that AKI, and this is the direction cosines. And the direction cosines has important properties that can be discussed. But here, the important thing is that I have now been able to write this as AKI XI. And so the properties of direction cosines take this form. So I have AKI, which has 9 components, but only 3 are really independent. So AKI times AJI is the Kronecker delta. That's the first property. Okay. And this is the same thing as saying, or A transpose is the identity matrix. Same thing. Okay. So let's look at what will happen if I have a rotation about x3 of theta. So what does that mean? I have this vector, this Cartesian system x1, x2, and outer plane is x3. And I want to rotate it to the new system x1 prime, x2 prime. And my goal now is to figure out how to relate a vector, a position vector, in this system R, this vector R, from this system C to C prime, right? And let's say this rotation is theta. Well, very simply, all you have to do now is calculate the angle between x1 and x1 prime and so forth to figure out the relationship right here, right? That's the relationship we found. So let's populate that so you can see how that works. And I'm gonna find what A is first. So let's walk it through. So the cosine, and let's start with this term right here, which is 1, 1. So what is the angle of E1 here? So E1 and E1 prime. So what is the angle? The angle is theta. So clearly that's theta. And then what is the angle between, and I can keep now going through each of them. So what is the angle between E2, for example, E2 right here, and E1 prime, E1 prime. So this one right here. So clearly that angle is a cosine of 90 minus theta. And then what is the angle between E, right? So E1, okay, right here, and the 3 direction, which is out of plane. So that's the cosine of 0. I'm sorry, that's 90 degrees, cosine of 90 degrees. And so I can continue on and fill this out, and I'll get minus sine theta here. I'll get cosine theta here. I'll get 0, 0, 0, and then let's do this one here. So what is the angle between E3 and E3 prime? Well, it's still aligned together. We didn't rotate that one. So that'll be cosine of 0, which is 1. So there you go. That's how you find the direction cosines for a rotation about theta. You can then do rotation about x2, which we call beta instead now. So if you do that, you'll find A equals cosine beta 0, sine beta, so that's a negative, 0, 1, 0, sine beta, 0, cosine beta. And then I can do a rotation about we can do a rotation by x1 now of an amount alpha, and you'll find that A equals 1, 0, 0, 0 cosine alpha, sine alpha, 0 minus sine alpha, cosine alpha. And so that's how you find these transformations that allow you to go from one coordinate system to the next. So in other words, if I know this vector here in one coordinate system, I can transform it to a different coordinate system. So what is the definition of a tensor? What is the definition of a tensor? A tensor is a system whose components obey a certain law of transformation when the independent variables undergo a linear transformation. So that is really what a tensor is. And so anytime you have a tensor, and a tensor is a system whose components obey a certain law of transformation when the independent variables undergo a linear transformation. And I just showed how to do that in a simple way. So another definition that I want to provide is a first order tensor. And vectors are one such quantities. This is a system of order 1, and it may be defined to have 3 components. In xi, and so let's call it bi, and 3 components, and I should say 3 components in C, so you remember that was a Cartesian coordinate system, and 3 components in C prime, if you recall. So I will call that bi prime. Okay, and if I'm able to do this transformation, bi prime equals aij bj, and the functions bi and bi prime are components in their respective coordinate system. Okay, and so this will allow us to define what a tensor is for the first order tensor. Now let's look at a second order tensor. In a second order tensor, we consider the outer product and we consider the outer product of 2 vectors and I'll call it bi cj, and earlier I made a note that this could be bi cj ei with a symbol like that, ej denoting outer product. Okay, so these are the components of the second order tensor. Okay, and so if I consider 2 vectors of this manner, the component of this system in a different coordinate system will look like this. So I define this in C, and then, sorry, not C prime, but C. which is this right here, this C right here, the one here. And I want to find the transformation in a new coordinate system, C prime. What is it in C prime? And so what I can do now, I can write what BI prime is and CJ prime. So I know how to transform BI. And BI prime is AIK BK. And I'll use K here for summation. Times. And then now I have to substitute what this transformation looks like. And that will be again A, J. I have to use a new variable now. I cannot use the same L, C, L. And again, this, and you know, I use this big C here, meaning intending to say Cartesian coordinate system, but in this example, I use C also. So let's be careful. There is not the same C. This is meant to be Cartesian coordinate system, and this was the actual vector C. So I apologize for using the same variable. But when I perform this, I get AIK, AJL, BK, CL. This is how you do a transformation of a second order tensor. Hence, if I were to call this BIJ, which is a 3 by 3, then I really have AIK, AJL, and then I'll call this BKL. And so this is how you, for example, transform a stress. And you may be used to doing it for example, a stress tensor. And you probably learned the Moore circle, but this is one way to do that, to transform a second order tensor. And so this is the same thing as writing in this manner. B prime equals A times B times A transpose. So if I have, and these are direction cosines, by the way. This is right here, the direction cosines that we had defined earlier. Okay. And so I can continue now doing that even for fourth order tensor. And you know, it's perfectly possible to do that. I have an important tensor property. I want to discuss. Each component of a tensor in the different bases representation is a linear combination of the components in the all bases. And so consequently, if all components of a tensor are zero in the original system of variables, they're also zero in the new variables. Okay, so each component of a tensor in a different basis representation is a linear combination of the components in the old basis. Consequently, if all components of a tensor of a tensor R0 is what I meant here. In the original system of variables, they're also 0 in the new system of variables. And so that's very easy to prove, and it can be done. Okay, so let's consider a tensor of second order. And so let's say I have Dij and Bij as an example. And I want to be able to then show that C, which is Bij times Dij, I'm going to define it that way, is invariant and it won't change upon transformation. So a scalar quantity should not transform, like temperature should not transform when you do a coordinate transformation. That's what that means. So I already know how to transform things, and we learned how to do that earlier. So, but let's look at how to do Dij prime. We already know how to do that. I'll write the A's first, is my way of doing it, and then the D. And my next step is to write I here and J here. And then here I'll pick two variables that are not used and then put it here. So that way Ij is here and then the K summation here. And they'll transform a second order tensor from one coordinate system to another using the direction cosines that you learned about already. So now I have going to do the same thing with Bij prime, and I have A, IN, A, JN, B, MN. So here you can see again, Ij here, and then the M and N are here. And these are your direction cosines. And I'm trying not to use K and L because I'm using M and N here. So I don't want to repeat stuff. So if I want to do a transformation on this, I can do C prime. And then I will say, okay, well, if it's C prime, that must have Bij prime, Dij prime. So then I just substitute what Dij and Bij prime are. So let's first substitute each of this. So I have AIN, AJN, BMN, and I have AIK, AJL, DKL. Okay. I want you to notice now that AIK, these two right here, is Kronecker delta. And I want you to show that, but it is Kronecker delta, del Kn. And this right here is also Kronecker delta, and it's del and L. Now N is repeated here and here, and then the K is repeated here and here. So I can collapse them. So I get B. So again, you can see here, this N repeats there. So then I get B, M, L, and I get D, M, L. So clearly, I got the same answer. This is C, isn't it? So when I transform C prime, I still got C, right? If it's a scalar, if it is a scalar, zeroth order tensor. So let's continue now then with some tensor calculus really quick. So let's look first at the gradient of a scalar. Tells you how that quantity changes, right? So then I have gradient of phi, and phi is my scalar. This is the derivative of phi respect to xi. Ei becomes a vector. The gradient of a scalar becomes a vector. Or I can also write it in a more compact manner, gradient of phi equals EI phi comma I. And if I want to know what is the change of phi in the direction n, where n is a unit vector, I can do that. I just find the dot product of del phi with n. That's how you do that. But I know that del phi is EI phi comma I. So the dot with n becomes nj, ej. And so then I get phi comma I nj. And the dot product EI dot and EJ dot, this is Kronecker delta. But you can see here j repeats, so I get phi comma I and I. So that's how you'll find them. The gradient of a vector becomes, the gradient vector is A. So I want to know the gradient of A. And I already know how to do that. I want to get A, I comma J, and this becomes a second order tensor. So we can also find the divergence of A. And that's how you find the divergence of A, the dot product. So you have, in this case, we know is EI, something comma I. So that's what this represents. We're dotting that with AJ, EJ, which is this vector A, represented in the Cartesian coordinate system C. And so now I can operate, and you see that this right here and this right here, the dot product of these two right here becomes delta IJ. So I can operate this in here. So then I get A, J comma I, del IJ. The J removes, and then I get AI comma I. Or, yeah, so that's what we get. We can then talk about Gauss theorem, which we're going to be using a lot in this class. And I really want you to learn how to do this because it will be used over and over and over. So say I have a body of volume of some kind. And there's a quantity here called T. So if I have the triple integral over this volume, T, and I have a bunch of, is an nth order tensor, comma I d omega. This is very powerful. Basically, we're going to show that I can represent this quantity somehow on the surface. So these are volume quantities, stuff happening inside, but I can somehow represent it in this on the surface. So this actually is a double integral, and the way it works, you remove this comma I and replace it with Ni ds, and that's how you do it. Now, I want to teach you how to do that with integration over parts, because that's what Gauss theorem is. I took a volume quantity and converted to surface, the surface integral. And so that's the boundary of this volume is a surface. And so that's a physical meaning.
I know the gradient of the quantity inside the body, and I'm trying to relate it to what's going on the surface, which is incredible that I can do that. To do this operation, what I want you to learn now is multiply. Here's a one times something. So you put the thing on the left-hand side and this on the right-hand side. And I'm going to integrate by parts. So I'm going to put the comma I over here and remove it. And then I'm going to put an error like that. And the error is n, I, whatever I remove, I put it here, plus, and then minus. This is how you're going to integrate by parts and learn how to do that. I don't want you to memorize this formula because we're going to do much more complicated calculations. The derivative of 1 is 0, because that's what this means. The derivative of 1 is 0. So I multiply, this goes back into the triple integral. So that's how that works. Negative TABC times 1 comma I, but this is 0. And this becomes, this cross term becomes plus, and now that goes into the surface integral. This is the boundary term right here. That's a boundary term. And what is a boundary of a volume? It's a surface. So that's TABC NIDS. So I've shown you how this becomes just that by integration by parts.